We're going to talk about using the Taylor series to evaluate limits. So let's start with that. And let's say the limit as x approaches infinity, nope, x approaches 0 of e to the x minus e to the minus x all over x. So when you do this, what you want to do is you want to look at the limits, and you're supposed to use Taylor series. So you don't have to build the series. You can use the table to look at the series. Can be written as the series from n equals 0 to infinity, x to the n over n factorial, which is 1 plus x squared over 2 factorial plus, that's a terrible looking plus, x to the 3 over 3 factorial plus dot 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 plus x to the n over n factorial plus dot dot dot. Now e to the minus x says we're putting a negative x everywhere there's an n. So, I'm sorry, everywhere there's an x. So we have negative x to the n over n factorial. Well, when you put in 0, anything to the 0 power is 1. And when you put in negative x, that gives you a negative x here. So let's take out the plus and put in a minus x. And then negative x quantity squared would be positive x squared over 2 factorial. And then negative x quantity to the third becomes negative x to the third over 3 factorial plus dot 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 plus negative x to the n over n factorial plus dot dot dot. So you want to look at these two expansions, and this problem says to subtract the two expansions and then divide by x. So we're going to say the limit as x approaches 0, and we have e to the x, which is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot 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 plus x to the n over n factorial. I don't know why I did that. Minus, and then we're going to pick up with the e to the negative x, which is 1 minus x plus x squared over 2 minus x to the third over 3 plus dot 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 plus negative x to the n over n factorial. And all of this is over x. So we're going to kind of look at what this looks like and build our patterns. So here I have 1 minus 1, which is going to cancel. And this one becomes x minus a negative x. It's actually going to double. And x squared over 2 minus x squared over 2 is going to cancel. And this x to the third minus x to the third is going to double. So let's start building that pattern. So I'm going to have 2 times x plus x over 3 to the third factorial, plus I would have x to the 5 over 5 factorial, plus x to the 7 over 7 factorial, plus dot dot dot, all over x. Well, we can go ahead and say in our dot dot dot, let's add to this. We know that we will have x to the n over n factorial if n is an odd number, all over x. So let's divide all of these terms by x. So we're going to have 2 times x divided by x is 1. This becomes x squared over 2 factorial plus x to the 4th over 5 factorial plus x to the 6th over 7 factorial. You don't really have to put that. We're going to say plus dot dot dot. Now, as x approaches 0, you can see that this is a nice, really pretty problem. So when I plug in 0, this goes to 0, this becomes 0, this becomes 0, this becomes 0, and so forth for all of them. So the limit is 2. So it's a nice, simple problem. The key to these is to make sure that you're using the series that they've given you and the binomial expansion. So this next one, it says the limit as theta approaches 0 of sine of theta minus theta plus theta to the third over 6 all over theta to the fifth. So you need to look at the fact that sine of theta equals x minus x to the third over 3 factorial, and it's an alternating series, plus x to the fifth over 5 factorial, minus x to the seventh over 7 factorial, plus dot, dot, dot. So we're going to say the limit as theta approaches 0. So we're going to plug in our sine of theta, only I called it sine of theta up here and I used an x. So it won't let me change it. I'm not sure why. There we go. So this was sine of x. We're going to use sine of theta down here correctly. So we're going to say theta minus theta to the third over 3 factorial plus theta to the fifth over 5 factorial minus theta to the seventh over 7 factorial. Let's go ahead and put plus dot, dot, dot. And then we have minus theta plus theta to the third over 6 all over theta. So this is our sine piece right here. Now, if you look carefully, theta minus theta cancels out. Nice and pretty. Also, if you look at the 6 factorial, I'm sorry, the 3 factorial right here, the 3 factorial is 6. So theta to the third over 3 is 6. So these two cancel out as well. So we have the limit as theta approaches 0 of theta to the fifth over 5 factorial minus theta to the seventh over 7 factorial plus dot, dot, dot. Let's go ahead and write plus theta to the ninth over 9 factorial following the pattern, minus theta to the 11th over 11 factorial plus dot, 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 all over theta to the fifth. Now you can see that the highest degree in the top is theta to the fifth. So let's go ahead and divide by theta to the fifth. So that means I have 1 over 5 factorial minus theta squared over 7 factorial plus theta to the fourth over 9 factorial minus theta to the sixth over 11 factorial plus dot, dot, dot. So when theta approaches 0, that means this approaches 0, this approaches 0, this approaches 0, and so forth. So our answer is 1 over 5 factorial. 5 factorial is, I think it's 120. Let me think about that for just a second. 5 times 4 is 20, times 3 is 60, times 2 is 120. So you can say 1 over 5 factorial or 1 over 120. So no matter what you're given, just use it appropriately. I would make a note to remind you, if you have, for example, if you have sine of x squared, then you want to start with the fact that sine of x equals x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. And then you put your x squared in. So sine of x squared means you're going to put an x squared everywhere there's an x. So we're going to take x squared and raise it to the third power over 3 factorial, plus we're going to take x squared and raise it to the fifth power over 5 factorial, minus we're going to take x squared and raise it to the seventh power over 7 factorial, and so forth. So sine of x squared as a series is x squared minus, this becomes x to the sixth over 3 factorial, plus x to the 10th over 5 factorial, minus x to the 14th over 7 factorial. So that should help you figure out how to do your limits according to and using Taylor series. So let's look at another one. It says the limit as x approaches 0 of the natural log of 1 plus x squared over 1 minus cosine x. Now, if you plug and chug, like you should start with limits, you have natural log of 1, which is 0, over 1 minus 1, which is 0, in determinate form. Now, I love L'Hopital's rule, but factor and cancel doesn't work here. So Taylor series gives us another method to evaluate these indeterminate limits. So let's look at, before we get into the limit, let's look at the natural log. And natural log of 1 plus x is the series of x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus dot dot dot. Now, I don't have these memorized. I'm reading them off of a table like you could. And so now let's look at natural log of 1 plus x squared. So what happens is in place of x, we're putting x squared. So we have x squared squared over 2 plus x squared to the third over 3 minus x squared to the fourth over 4 plus dot dot dot. We'll squeeze those in. So then this is x squared minus x to the fourth over 2 plus x to the sixth over 3 minus x to the eighth over 4 plus dot dot dot. Now let's make a note of what cosine of x is. So if we look at the table, cosine of x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the eighth over 8 factorial minus dot dot dot. All right, so we're going to look at this limit, and it says the limit as x approaches 0. To have it right in there, isn't it? The limit as x approaches 0, and the numerator is the natural log, which is x squared minus x to the fourth over 2 plus x to the sixth over 3 minus x to the eighth over 4 plus dot dot dot. And then in the denominator, we have 1 minus, and our cosine is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the eighth over 8 factorial minus dot dot dot. So I'm going to distribute this negative. You can see the negative being distributed here. And then 1 minus 1 cancels. And we could skip that step, but I want to make sure that you understand why it happened. So now we have the limit as x approaches 0, and we have x squared minus x to the fourth over 2 plus x to the sixth over 3 minus x to the eighth over 4 plus dot dot dot. And in the bottom, we have x squared over 2 factorial minus x to the fourth over 4 factorial plus x to the sixth over 6 factorial minus x to the eighth, the x to the eighth over 8 factorial plus dot dot dot. Now you can see similarities here. Do you see the similarities? Because there should be. It should help you out in some point. Okay, so when we look at these similarities, we can pull an x squared out of both. So let's say the limit as x approaches 0. And so when I pull out an x squared, on the top I'm going to say x squared parentheses 1 minus x squared over 2 plus x to the fourth over 3 minus x to the sixth over 4 plus dot dot dot. And on the bottom, we have x squared. Let's put that back in green. So we have x squared times, now when we factor out the x squared, we have 1 over 2 factorial minus x squared over 4 factorial plus x to the fourth over 6 factorial minus x to the sixth over 8 factorial plus dot dot dot. Now these x squareds are the GCFs of the two lines, so they cancel beautifully. So now let's write this out one more time. So the numerator says 1 minus x squared over 2 plus x to the fourth over 3 minus x to the sixth over 4 plus dot dot dot. And the denominator says 1 over 2 factorial minus x squared over 4 factorial plus x to the fourth, not 6 there, x to the fourth over 6 factorial minus x to the sixth over 8 factorial plus dot dot dot. Now, our limit as x approaches 0, so that means this approaches 0, this approaches 0, this approaches 0, all of them approach 0, and the denominator as well. So our limit is 1 over 2 factorial, which equals 2 factorial, which is 2. This helps us see that we can use our Taylor series to evaluate indeterminate forms and limits. So it can be a very helpful tool, and it's not overly hard. It's just interesting numerically. So I hope you have a great day. And if you have any questions, let me know. Thanks.